Good morning, champs. In a previous video, we explored how to transform a triple integral from Cartesian coordinates into cylindrical coordinates. Specifically, we focused on boundaries for a cylinder, but here's the catch. Cylindrical coordinates aren't just for cylinders. They work for any shape with axial symmetry. In this video, we'll dive into some examples to see their versatility. Here's the 4-step approach we'll use. Step 1. Check for axial symmetry. Step 2. Express the radius as a function of z, written as r equals f of z. Step 3. Write the boundaries for height z and angle phi. Step 4. Set up the integral. Let's get started. Let's look at a classic example. The paraboloid. It's actually symmetric around the z-axis, so we're good to move forward. The function for the paraboloid is z equals x squared plus y squared. In cylindrical coordinates, where x squared plus y squared equals r squared, this transforms into z equals r squared. Rearranging, we get r equals the square root of z. Notice that the radius changes as z changes. This is key when defining the domain. Here's what the domain looks like. For z, 0 to h, where h is the maximum height. For r, 0 to the square root of z. For phi, 0 to 2 pi, for a full rotation around the z-axis. And there you have it. We've set up the boundaries for the paraboloid in cylindrical coordinates. Let's move to the next example. Next, let's look at a cone. Just like the paraboloid, the cone is actually symmetric around the z-axis. This cone has a height, h, and its radius depends on the height. At the top, where z equals h, the radius is r. At the bottom, where z equals 0, the radius is 0. The radius grows linearly with height, so the relationship is r equals r over h times z. Here's the domain for the cone. For z, 0 to h. For r, 0 to r over h times z. For phi, 0 to 2 pi for the full rotation. That's it for the cone. Now let's move on to summarizing everything. Let's quickly recap what we've covered. We explored how cylindrical coordinates work and when to use them, focusing on shapes with axial symmetry. Here's a summary. For the paraboloid, z goes from 0 to h. R goes from 0 to the square root of z. Phi goes from 0 to 2 pi. For the cone, z goes from 0 to h. R goes from 0 to r over h times z. Phi goes from 0 to 2 pi. Remember the 4-step process. Step 1. Check for axial symmetry. Step 2. Express the radius as a function of z. Step 3. Write boundaries for height and angle. Step 4. Set up the integral. That's the framework. Now, let's dive into a practical application. Now it's time for a practical example. Here's the setup. We have a partial paraboloid filled with gas. The gravitational field varies with height z and is given by g of z equals g naught times 1 plus z over h. Here, h is the maximum height of the paraboloid. The energy density at any point is a rho times g of z times z. Our task is to calculate the total energy using a triple integral. Step 1. Convert to cylindrical coordinates. The paraboloid equation z equals x squared plus y squared transforms to z equals r squared in cylindrical coordinates. Rearranging, we get r equals the square root of z. The boundaries are, for z, 0 to h. For r, 0 to the square root of z. For phi, 0 to 3/2 pi, because we only have 3/4 of the paraboloid. The energy density function becomes rho times g naught times z times 1 plus z over h. Step 2, set up the integral. The total energy is given as following. Step 3, solve the integral. After solving, the total energy stored is 7 pi over 16 times h cubed times rho times g naught.